This water tank was in our neighborhood, and I knew that in our neighborhood we get a lot of wind. So I began to wonder, how fast would the wind need to blow in order to knock over this water tank? And we do get lots of wind, so it really was a real concern of mine. But notice what happens when the wind blows. That force of the wind would cause that thing to rotate. And that's a little different than other forces that we've looked at. The forces we've looked at before have just made something move in a line. Now we're looking at forces that will make something rotate. And to understand that rotation, I just have a meter stick right here. And right here at the 50 centimeter mark, I drilled 2 holes through it and put a stiff wire hanging from a string there. And right here, I've got 200 grams at 20 centimeters from this pivot point, and I've got 100 grams over there at 40 centimeters from the pivot point. So the effect of having 200 grams at 20 centimeters is balanced by the effect of having 100 grams at 40 centimeters from the pivot. And notice here that from here to here I have half as much mass, but it is at twice as much distance. So when that happens, if you could take the mass and multiply it by the distance, you get this number, and this mass times that distance is the same number. So it looks like it's balanced. In this example, I've got 500 grams, or I should say, the effect of having 500 grams at 5 centimeters is balanced by the effect of having 100 grams at 25 centimeters. And here, this mass here, this is 1/5 as much mass, and I've placed it at 5 times the distance. So again, mass times distance is this number, mass times distance is that number. Well, this effect that we're talking about has a term, and that term is called torque. And we abbreviate it with the letter T, although that is a Greek letter T named tau. Torque is calculated by the force multiplied by the radius that is perpendicular to that force. So this is our symbol for perpendicular. That force is pulling down here, and the radius or the distance is perpendicular to that. If we're going to be consistent with our units, we really should measure the force in newtons, and we really should measure the distance in meters. I put newtons on the left and meters on the right, which is different from here. So I probably should say meter newtons, but it tends to flow off the tongue a little nicer if we say Newton meters. So I can convert grams into kilograms and then multiply by 9.8 to turn it into the weight. Okay, so that's what I'm going to do here. I'm going to take 500 grams, I'm going to divide by 1,000 to get into kilograms, multiply by 9.8, and that right there has turned it into newtons. Same thing on this side with the 500 and this side with the 100. And then the 5 centimeters, we really should have measured that in meters. So I'm going to divide both sides by 100 to get it into meters. And, it's going to still stay balanced. And the reason is that 1,000 is on this side and 1,000 is on this side of the equal sign, so it cancels. Same with the 9.8, same with the 100. So it really was okay to take grams and multiply by centimeters and have equal grams multiplied by centimeters, because it really is newtons times meters and newtons times meters. But just to be clear, it is totally wrong to talk about grams as a force. Okay, it's totally wrong to do that, but as long as we know that it is wrong and we do it anyway, then it's okay. And please don't take that as a life philosophy. It's not that bad, because it really does work out mathematically to be the same in this situation. So here we have the y-axis and the x-axis, and to the right was positive, left is negative, up is positive, down is negative. Well, similarly, we're going to have torques that are positive and negative. So if I had this force acting at this radius, and those are perpendicular, that pulling down here is going to make this meter stick tend to rotate in the same direction as a clock. So we call it clockwise. And this mass over here pulling down at this distance, pulling down over here, is going to tend to make this rotate counterclockwise, so the opposite direction of a clock. Now with this, right was positive, left was negative, up was positive, down was negative. Which of these do you think is positive or negative? Do you think clockwise is positive or is it negative? Well, I bet you if I told you that clockwise is negative, you'd be very disappointed that you would think clockwise should be positive. It's not. So we could either just get over it, or we could just kind of understand that it is a convention, that we just agreed this is the way we're going to do it. And for no other reason, that's the reason we're going to do it. Well, I say there's no other reason. It is actually kind of based on a screw. And what we may have learned is that righty-tighty, lefty-loosey. So if I stand over the top of that screw and I look at that as I turn it to the left, okay, that would be counterclockwise. That is going to loosen that screw, and the screw is going to move in the up direction. So a positive torque moved the screw in the positive direction. Similarly, if we go righty-tighty as we tighten that thing, if we move it clockwise, that screw is going to move down, so a negative torque moved it in the negative direction. Okay, so if this is the x-axis and this is the y-axis, this is going to be the z-axis, but which of these is going to be positive and which is going to be negative? It's still going to be based on this idea, that if I had a screw here and I do righty-tighty clockwise on that, that would be a negative torque, and the screw would tighten, it would go into the wood, so a clockwise or a negative torque moved the screw in the negative direction. That's the negative direction. Okay, it is consistent. Now, we talked about equilibrium a little while ago, and we didn't talk about the first condition of equilibrium. We just talked about equilibrium, and that's because we didn't know there was more than one condition of equilibrium. But we did this problem where we said that the sum of the forces are equal to 0. The sum of the forces in the x direction equals 0, and the sum of the forces in the y direction are going to equal 0 if it's in equilibrium. So if this big old chandelier is being pulled up in that direction and being pulled in that direction and pulled in that direction, to be in equilibrium, the horizontal forces must add to 0 and the vertical forces must add to 0. So we take that and we find components of it to the left and to the right. And once we show components, we get rid of that one so we don't count it twice. But it looks like the pull to the left added to the right, left being negative and right being positive, add to 0. And up added to down, where down is negative, also adds to 0. So this right here guarantees that this thing is not going to be accelerating left or right. This is going to guarantee that it is not accelerating up or down. What do you think the second condition of equilibrium is going to guarantee? Well, the second condition of equilibrium is going to be that the sum of the torques equal 0. And that's going to guarantee that it is not accelerating clockwise or accelerating counterclockwise. If the sum of the torques is 0, it's not going to be accelerating angularly. It's not going to begin rotating faster or slower or in different directions. So here I have two masses on this side balanced by 1, and it looks like it's just there in equilibrium. So let's just check to see that the sum of the torques do equal 0. So this here is a counterclockwise torque. It's positive, and this would pull this down, making it tend to rotate clockwise. So that would be negative, and that would be negative. So this force times that distance would be a positive torque. This force times that distance would be a negative torque. This force times that distance would also be a negative torque. So that times that is this, that is this is this, and if we look at that, it really does add to 0. Well, here's the typical problem here. Let's say we have this person painting a mural, and they're standing on this scaffolding. And what we want to do is figure out how much force this board puts on that little bar right there and how much it puts on that little bar right there. Remember, we have two conditions of equilibrium. But if this person weighs 150 pounds and they're standing right in the middle, we are going to say that the board is 10 feet across, so 5 feet from this side and 5 feet from that side. if they're standing right in the middle, it's not surprising from the first condition of equilibrium that each of these has to be 75. 75 pushing up and 75 pushing down, and 75 pushing up and 75 also pushing up, and 150 down, that was negative. They should all be balanced. Otherwise, they'd be accelerating in the up or down direction. But let's also check that in terms of the balancing of the torques. Now, this is an important idea. There's not a clear pivot point on this picture. So I can arbitrarily pick where I want the pivot point to be. To me, maybe it makes sense to put the pivot point right over here. It just gives me a way of measuring distances so I can calculate the torque. And I'm going to do it a couple different ways to show you that it really is arbitrary where we place it. So if I put the pivot point right there, that force doesn't provide any torque. Okay, to provide a torque, there has to be some distance, and there was no distance between that force and the pivot. It went right through the pivot. So this is a force that's acting at 5 feet, and that's going to be a negative torque because it's clockwise. This is a force that is acting not 5 feet, but 10 feet, and that's going to be lifting up, tending to make that rotate counterclockwise. So this was a negative torque. This was a positive torque. This times this is 750. That times that is positive 750. They add together to equal 0. So yes, it does look like the forces in the y direction were equal to 0, and the sum of the torques was equal to 0. I guess I just wasn't even considering the sum of the forces in the x direction. But now let's change it up a little bit. Let's move this person over here to the right some. And so they're going to be 7 feet from the pivot point here, and this is not 3 feet, but 10 feet from the pivot over here. Now it might stand to reason that when this person gets closer to the scale here, there's going to be more force on it than when they were standing here. They won't be equal anymore. But if you're tempted to approach this problem through proportions, you're really going to mess yourself up. Students really tend to like using proportions, but you'll mess yourself up. We have a better tool than that. So let's try the sum of the torques. So this force of her pulling down at 7 feet is a clockwise or a negative torque. This scale pushing up at 10 feet would be a counterclockwise or a positive torque. So this negative torque added to this positive torque. We don't know what the force is, but we do know that those two torques must add to 0. Okay, so I can take this times this, move it over here, it becomes positive, and then divide both sides by 10, and I would find that the amount of force right here needs to be 105 pounds. Now I need to find out how much force was over here. It didn't provide torque because it was at 0 distance to the pivot, but it did provide force. So we can use the first condition of equilibrium to find that. It's just that gravity pulling down with 150 pounds and the scale pushing up with 105, and then whatever this is pushing up, all three of those forces added together should equal 0. So I can solve for question mark, and I would find that it was 45 pounds. So this was 105 pounds, this was 45 pounds, and let me reinforce the idea that the pivot point is arbitrary. We could have picked it anywhere. So let's just pick it somewhere else and see if we get the same numbers. So if this is the pivot point, the force of gravity pulling down on her right through the pivot point, that's not going to provide any torque. But now this force acting at that distance would tend to make this rotate clockwise. So that one's going to be a negative torque. So first of all, the sum of the forces, if this is question mark, this one should be 150 minus question mark. Okay, just the up equals down. So now let's go ahead and do our sum of the torque problem. It's going to be just a little more algebraic, a little more mathy, but we can do that. So here's our pivot point. we've got 150 minus question mark, and that is at a distance of 7 feet. So distance times force, and that was negative because it was clockwise. This one pushing up here is going to tend to produce a counterclockwise or a positive torque. So question mark times 3 feet is the torque that the other one produces. Now the only thing we have to remember here is that we have to distribute the negative 7. So negative 7 times 150 is negative 1050. Negative 7 times negative question mark is positive 7 question mark. And then 3 question mark as well. We can combine like terms here and get 10 times question mark. And this term can be added to both sides. It comes over here. Divide both sides by 10. And we find that the answer was the same as what we found before, that was 150. And then if I take 105. If I take 150 minus 105, then that's where I get my 45. So it really doesn't matter where we choose our pivot point. We could have done it over here or somewhere in the middle, and it all would have worked out just fine. So this one's a little more complicated because this time the forces are not just in the up and down direction. But when you hang a door like this, these hinges are holding the door stationary, in equilibrium. So we've got the weight of the door, the force of gravity pulling down here. And so there is a force pulling in the down direction. We need an equal amount of force holding that door up. And so each of these hinges is going to be holding the door up with half the weight. This holds half the weight, this holds half the weight. So those two minus this one is going to equal 0. Now that's not the only forces, because if we were to like hold this here and unscrew this hinge, the door would swing to the right down here. So that hinge must have been pushing back off to the left. Or if we were to keep this screwed in and unscrew this one, the whole door would fall over that way. So this hinge must have been holding it back that way. And we see from the first condition of equilibrium that the sum of the forces in the x direction also equals 0. This is a positive force to the right. This is a negative force to the left. Those are the only forces in the horizontal direction, so they add to 0. And so if I find out what this one is, this one would be the same. But I'd like to go ahead and find out what that one is once I have some numbers to work with. But if we now need to look at the second condition of equilibrium, see if all those torques balance to 0 as well. So I'm going to arbitrarily pick my pivot point right there. I could have picked it here, I could have picked it there, I could have picked it anywhere, and the math would still work out. By picking my pivot point right here, this force, and this force all produce no torque, because those forces go right through that pivot point. So these are the only two that produce torque. So that force is acting at this distance, this force is acting at that distance, and so this would be a clockwise torque, so negative, positive, and if I gave you numbers here, where we see that this distance here is 1/3 what this distance was here, that means this force should be 1/3 what this force was, or that force times this force, and this force times, an unknown force times that, one of those being negative, we could solve our equation. Now, torque is really useful in solving for the center of mass. In this picture, in my previous pictures, I had it hung right there at 50 centimeters, right there in the middle. But now I have this hung over here at 70, and I had to add a little weight to keep it balanced. And I want to find the center of mass of that meter stick. And that's all I know. All I know is that I've got 200 grams, 13.2 centimeters from the pivot, and I want to find out the mass of that meter stick. So that's the 70 centimeter mark. 70 centimeters of stick is hanging off to the left, 30 centimeters are hanging off to the right, but it's easier than that. The center of mass of this thing is going to be in its middle, in its geometric center. So the mass of that entire meter stick is right there in its middle, and that is 20 centimeters from this, so 50 and 70, it's 20 centimeters away. So it just turns out that this produces a positive torque, this produces a negative torque. We take 20 times question mark minus 13.2 times 200, and we multiply that out, we get this. We move this to this side, it becomes positive. We divide both sides by 20, and it looks like the meter stick is going to be 132 grams. We're just saying that the center of mass is the place where we can think of as if all the mass is right there. So now we're going to find the center of mass of this juggling pin. And there's mass right here, real close to the pivot point. There's mass way over there, real far from the pivot point. But the center of mass is the place where I can think of as if all the mass of that juggling pin is at one location. Where is it all balanced out? So I've got 200 grams at 30 centimeters, and it's balanced by 162.4 grams. I just put that on a scale. And I want to see, where is it like all that mass is? What's the distance to the center of mass? Well, this is a positive torque. This is a negative torque. I still get confused with clockwise and counterclockwise, because who has an analog clock like that anymore? I guess classrooms. Okay, but this positive torque added to this negative torque should equal 0. So I multiply those out. This is a negative. I'm going to bring it over this side, and then I'm going to divide both sides by 162.4, and I find that 36.9 centimeters from the distance from the pivot point should be where that center of mass is. So right there is about where that center of mass is. Now I want to find the center of mass in a very different way. It's a very powerful way, because I don't know anything more than the dimensions of this shape. Okay, I don't know the mass of it. I don't know the thickness of it. I don't know the density of it. I don't know any of that. All I know is its dimensions. And I want to find the center of mass, knowing only the dimensions. So yeah, I could find the center of mass if I hung a known mass over here and did like just the previous problem. But I want to teach you a powerful way to do it without actually physically setting it up. We're just going to use this idea to calculate it. Well, clearly the thing would be balanced if I had an identical shape exactly on the other side there. And we're trying to find out how far from this end can we think of as if all that mass is acting. Well, instead of putting an identical shape in there, let's replace that shape with this shape, and this shape. Well, it's essentially the same thing. And I'm showing the mass of this yellow rectangle in here, but we don't know the mass of it. But the mass is going to be directly proportional to the area of that shape. So because this has a really big area, it's also going to have a much larger mass. So we don't actually have to know the mass. It's just going to be proportional to the area of those rectangles. And if it's a rectangle, well, the center of mass is going to be right in the middle. So if this is 30 centimeters across, the center of mass is going to be 15 from there. This was 10, so its center of mass is 5 to here, but plus the 30 we already were, it's going to put it at 35. And that would also produce a negative torque. And this nice rectangle here, we can break it up to there as well, and it's going to be 45 centimeters from the end. So the area of this one is 90, 10 and 12 is 120 square centimeters, and this is 240. So 90 plus 120 plus 240, the whole entire area is 450 square centimeters. So this 450 centimeters at an unknown distance produced a positive, square centimeters produced a positive torque, and then we had 15 in this area, 35 in this area, 45 in that area. They all have negative torques. So we just can put them all together like this. And then to solve for this, these two got moved over, or sorry, these three got moved over to that side, and then we divided by 450. And when we do all that out, we find that the average distance would just be 36.3 centimeters. This is the equation that calculates for that, and it might be a little scary, but it is just the first mass times its distance, plus the second mass times its distance, and the third mass and the third distance, and so on, divided by the total mass. And that's what we did. We took mass, which is proportional to area, mass times distance, plus mass times distance, plus mass times distance, and we divided by the total mass to find the center of mass. And that's pretty powerful. So if this is a carpenter square and you have a pegboard like this, and there's usually a little hole right here where you can hang that on your pegboard. But let's say the way our pegboard is arranged, we want this thing sitting like this and hanging and not twisting at some angle. So we got to drill a hole there. Yes, we could put our finger there and balance it, and we would get pretty close, but we can do better than pretty close. We can actually calculate it. So the area of this shape is proportional to that, the mass of that shape, and the area of that shape is proportional to the mass of that shape. And I want to figure out how far over and how far down to do that. Okay, it's just going to be the mass of that times its distance, and the mass of this times this distance, those two added together, divided by the total mass. Okay, I'm not going any further with that one. So if I take a socket wrench here and I grab really close to the handle, well, the distance is short, so we won't get much torque. We can get more torque by putting our hand further away. But just this force times that distance would calculate the torque. I could get even more torque if I put a cheater bar over this, just a pipe slipped over the handle. Then I can get my hand really far away, and I've almost effectively doubled the amount of twisting force, the torque that I could get on there. But what if I had rotated my hand like this and pulled off in that direction? Well, I'm not going to get quite as much force because this force has to be perpendicular to the radius, that arm there. So what we would do is find a component of the force. How much force that I'm pulling here, how much of that force is perpendicular to that? Well, the force times the sine of the angle would give us this opposite side here. So in this situation, we could just take this distance times this force, which is this, and that would calculate the torque as well. So another way to calculate it, if it wasn't perpendicular. So this is when the force is perpendicular to the radius. If it's not, we just have to multiply by the sine of the angle to find the component of the force that is perpendicular to this. Okay, and that's an equation we'll be able to check off. Another way of doing this is talking about the line of action. That force is coming in this direction like this, and that force extends in this line. And you can extend it far enough until you get a component of the distance that is perpendicular. So if this is theta and this is the radius, the component of the radius is going to be just the hypotenuse times the sine of the angle. So that also says we can do it this way. So now let's look at this last problem here, and we are going to actually calculate how fast the wind would need to blow to tip this over. To do that, we need to first figure out how much force the wind would have to apply to tip it over, and we're talking about a drag force. As the wind drags across this cylinder here, it puts a force on it. So it's just a simple torque problem that this force acting at this distance and the weight of it pulling down here acting at that distance is going to provide torques. So just force times distance minus force times distance. In equilibrium, it should all equal 0. So that's the force that would just keep it in equilibrium. If the wind put more force on it than that, then it would tip it over. Okay, so that's how much force the wind would have to apply. Now we have to figure out how fast the wind would have to blow to make that happen. So the wind is blowing all on this area here, 29.3 square meters of surface area, and it's a cylinder, and this is the density of the air. So this is the equation we looked back when we did the projectile trajectory spreadsheet calculating the trajectory based on air resistance. That the drag force of air has to do with the shape of the object, called the drag coefficient, the area that the wind is blowing against, the density of the air, and the velocity of the air. So we know the drag coefficient for a cylinder, we know the area of the cylinder, we know how much force it needs to apply. We're just solving for how fast the wind would need to blow. And if I solve for V, it would be about 35.3 meters per second, or about 78 miles per hour. And that sounds fast, but where I live, it really can blow 78 miles per hour. And so it could blow over. That is what the weight of it is empty. And if you put 16,000 gallons of water, its weight goes way up to this. And I'm just doing the exact same calculation with this number now. And I find that if it's full, the wind would have to blow 227 miles per hour to knock this over. So as long as it's not empty, I think we're safe. That's a little bit about torque and rotation.